Hello, and welcome to our third lecture. And we're finally at the point of doing machine learning. I think that we've covered enough of the basics of Python to now just dive in and get started. So in today's lecture, we're going to introduce the notion of supervised machine learning. This is one of the three main subfields of machine learning, and it's what we will spend the majority of the semester on. So we are going to begin by just discussing what is supervised machine learning. Then we will build a general supervised machine learning framework, discuss model performance, make a quick note about underfitting and overfitting, and then move into our first real model called the single neuron model. And this model will we will adapt it to be called something called the Perceptron. And then we'll code it from scratch and then show that it's like magic. And it's my first machine learning algorithm that I ever programmed. And when I did it for the first time, I'll never forget that moment to see it actually work in practice. So I hope that you're excited about that. So what is supervised machine learning? Well, generally speaking, in any machine learning task, we're going to encounter measurements, signals, or features. And this data in supervised learning will be associated with some given label, right? Now, before we discuss what labels we have, just make this abstract model in your mind that there is a space of all possible measurements, which I denote by X. And then for all of those measurements, there will be some associated labels, right? And these labels are determined by some unknown target function, which I will always denote by F. This function is a theoretical function that always takes measurements of data, whether these are signals, whatever, and will always assign the correct label to those measurements. Okay, so it's a theoretical function, and it's truly unknown, and we'll get to more about that in a moment. So in supervised learning, this function is going to create pairs, where the X entry of these pairs is a measurement, and the Y entry is an assignment of that X value by the target function F. Okay, and those pairs, some of them we have. Okay, and this is an important point of supervised learning, that we have access to some of these pairs, meaning that we have measurements, some subset of measurements shown here in red. And then for each of those measurements, we happen to know the corresponding label for those measurements that has been assigned by the target function. Okay. So we're going to use these pairs of data, right, the measurements and the labels, to build a predictive model on unseen pairs of data. So this is a really important point. The whole purpose of machine learning is to use data to make predictions on data that we haven't seen yet, right? So if you look over here in the measurement space, we only have these certain like blobs of data, and we only have these labels over here. But we would like to use this to possibly make predictions on data that's not in those blobs, right? So what are the types of machine learning or supervised machine learning? Well, generally speaking, there's two types. If the label space consists of real numbers, then we're performing what's called regression. So this would be an example of regression where on the y-axis, we have a numerical label, and as input, we have some measurement of the data. And we're trying to find some function that's approximating the data in the space. Okay. If the space Y is categorical, then we're performing classification supervised machine learning. So this is what an image of classification would look like in 2D, right? So in this figure here, we have X1 measurement and X2 measurement, and then we have two different types of labels, and we're trying to somehow find a function that separates that data. Now, notice that in both of these cases, I said function, right? This is the general goal. We want to find a function that's approximating the data and behaves like that unknown theoretical target function. Which brings us to a general framework that we need to build up in order to understand the models that we're working with. So as I mentioned before, we have some unknown target function that always assigns the correct labels to any feature or any vector in X, right? So that function, because it assigns the correct labels to the features in X, provides us possibly with some data to work with. And this subset of data is what we were going to use for training the algorithms that we work with. Okay, so if we go back to this picture here, the X vectors are in the red blobs here, and then the corresponding Y values are in the blue. So that's what this sequence is here, these pairs of data. And again, these pairs of data were generated by the target function. So we hope to approximate that target function somehow. In order to do that, we need to choose a model and a learning algorithm that is appropriate. Now, we don't know any yet. We're going to learn one today. But as we progress throughout the semester, I'd like you to always reference back to this picture that we're building right now, because it's good to have a theoretical framework, and it just helps with the conceptual understanding of what you're doing. So this learning algorithm is going to choose from a set of possible hypotheses. And those hypotheses, of those choices, one of them will be an approximation to the function f that we're satisfied with. So the hypothesis set really is a space of functions, and the learning algorithm is looking into the hypothesis set and sifting through everything and trying to pick the best function out of that space that matches f as we observe from the training examples. So we're using the output of f in the y entries here as kind of like our guiding principle. We want, if we feed this x into our g, we want it to equal this y. And we want that to happen for any pair of those data. So, well, not any pair of those data. I mean, we want it to happen as many times as possible on the data that we have in front of us. But there's some caveats to that we'll come back to. But again, we're just trying to search through this hypothesis set, which is a space of functions, using a given algorithm. And hopefully we're going to find some function g that's approximating this true target function. So how do we evaluate the model performance, right? So if we have a possible g that we find in the hypothesis set, how do we know how it's performing, right? Well, there's many different ways to do that, but at the beginning of the semester, we're going to start simple. Okay, we're going to measure this, well, in general, not just at the beginning, but in general, we're going to measure model performance with a non-negative function. And this function should return high numerical values when the model is not approximating the target function well, and low numerical values when the model is a good approximation. So it's like we're penalizing the function or the model when the function that we generate g, if this is doing bad at approximating f, we want to penalize it and give it a higher value, right? So that's the whole goal of these what are called loss functions, right? So notice here, this is kind of a general looking function that this eta here can be any positive scalar that you want. It just depends on the task at hand, or even we can replace eta with a function of n, where n is the number of training examples that we're looking at. So for example, if eta was replaced by 1 over n, this loss function would be called the mean squared error loss function. But notice though, that in this difference here, we're squaring it, so that's going to be a positive number, right? But if g is equaling f for the data in question, this is always going to be 0, right? So if g is a good approximation to f, this loss function will be low, right? If g is a bad approximation to f, and this is not equaling, these aren't equaling in here, then the square term is going to make it positive, and we're summing over all the samples that we have in the training data, and it's going to be high. So our goal in general is to have a low loss function. Sometimes instead of loss, it's called a cost function. Okay, but in both cases, it really is just a way of understanding model performance. Okay, so next up, we should probably make a note about underfitting and overfitting. So I think the best way to illustrate this concept is with a graph that I generated using Python, and I'll provide the code for this in the description of this video and on Canvas for you guys to play around with. But in these pictures, we have sample data, like it's shown here in magenta, scattered throughout, right? And in orange, we have a hypothetical true target function for those samples, right? Now, the model on the left-hand side is a linear regression model, which we'll learn what that is next time. And that blue line is trying to approximate the sample data there. And it's not great, honestly. You can even see the mean squared error appearing above the figure. It's really not doing that great. But to contrast that, on the right-hand side, we have a polynomial regression model of degree 15. So it's like a really high degree polynomial. And we can see that this blue line, which is the model, is hitting every single point of data that we, well, pretty much, like, looks like 80% of the data it's hitting. So you might think to yourself, oh, this is great. Like it's doing well at approximating the data in question, right? However, we have to think back to the general framework that we developed earlier. We want our function that we find to be a good approximation of this unknown target function, not just a good approximation to the target function on a specific subset of data. We want it to be a good approximation over all data, right? So going back to this image, yes, we're hitting this subset of data here, but the true target function is shown in orange. And look right here. This model is performing horrible on this interval, right? We're supposed to be close to this orange line, but look at how high and how low the blue model is. And then over here, it's just terrible, right? Like if we encountered an X value right here, then the blue model would predict some drastically lower number than what it really should be. So this is overfitting. On the left-hand side, we have an underfit model. On the right-hand side, we have an overfit model. Now, this is a problem. This is a really big problem in machine learning, and it's really easy to forget about because a lot of the algorithms are just annoying to get working properly, and you spend a lot of time on setting it up, cleaning the data, getting it ready, and then running your model, and it's running well, and you're like, yes, this is good. But you have to always remember that you're only looking at some subset of possible features of data, and you have to be wary about what happens outside of that data that you haven't seen. I mean, outside of the data that you have in front of you, right? So this is a really important point, and we're going to discuss this in detail in another lecture. But I think it's important for me to at least make a note of this in the first real machine learning lecture that we have, so that you're aware of it and you don't get too excited when you have a model working and you think it's running well. So yeah, observable data is not always indicative of indicative of general data behavior, like over here, right? So,
Sorry, I have a quick question.
yeah,
On the previous slide, I think actually on slide 31, so why are the sample points not on the true target function? Because aren't those like theoretically like sampled or taken from that target function?
I I I couldn't plot it exactly the way I wanted to do it. I wanted to
Okay.
put some noise in there. Um,
Uh-huh.
I, I probably should have emphasized twice when I first brought this up that this was like a almost a true target function. Like
Okay.
it's behaving like the true target function does.
Okay.
That's what I meant to say. But thank you for bringing that up. You are correct. The true target function should, every single point, it should be there, right?
Okay. Cool. Thank you.
Um, and this is the thing about the true target function is that a lot of times it is it's like a weird piecewise, discontinuous, really messy looking thing, right?
Mm-hmm. Yeah.
And it's hard to um,
I plotted.
plot something, yeah, plot
Yeah.
something exactly like that.
Okay. That
But
makes
yeah,
sense.
thank you for bringing that up.
Yeah. Cool. Thank you.
Okay, so one way that we can kind of, in a very naive way, avoid over and underfitting is by partitioning the data that we do have into different sets, like a training and testing set. So typically you can use, if you have enough data, you can use maybe 75% of your data as the training, and you run your model on that, and then you see how it's doing on the data that you left out. So instead of having just training examples like this, we'll have like training and testing samples. And then later in the semester, we'll also do something called validation. So train, test, validate. But for now, we're just going to have we're going to take our data and split it into two sets, a training set and a testing set. And then when we finally produce our hypothesis G based off of the training examples, then we can evaluate that on the testing examples. Okay, then that's a naive way of doing it, and there's many different ways to do this, but for now, this is how we're starting. Okay, so we've made it to the single neuron model. Now, typically in a machine learning course, you will start with supervised learning from the standpoint of like an algorithm called k nearest neighbors, or maybe linear regression, like least squares regression, things like that. These are what I would consider like classical machine learning algorithms, and are really studied in so many different courses. I used to teach this course starting with those as well, but I think the best way for us to start is to kind of jump ahead and then come back to those classical algorithms. And we're starting with a single neuron model, which will build up into what are called neural networks. So just to preface the next, or to say something about the next few weeks, we're going to build neural networks first, and then go back to other types of supervised machine learning. So as with many of these machine learning algorithms, neurons and neural networks are function approximation models. And these can be used both in regression and classification tasks. And we'll see both early in the semester. And this is an important fact that not too many people think about. Neurons and neural networks really are generalizations of many of these classical supervised learning algorithms. So neurons can generalize linear regression, polynomial regression, logistic regression, and even support vector machines. So neural networks are one of the most general function approximation tools that we know of. And I'm excited to tell you more. And they look cool. Look at that. That's an awesome looking diagram. That's a neural network. You see we have layers, we have connections between the layers, and we'll get there. But first, we need to start with this guy. That one little node right there is called a single neuron. This is the neuron, it's outputting some value, and then it has 3 inputs. So this is the model we're going to start with. And once we understand how these things work from different perspectives, then we can start stacking them together and create very complex models. But we have to start small, I guess. Okay, so I have a little story to motivate the single neuron model. So imagine you are a very simple child or organism, very simple. And imagine that the only stimuli that you can take in are 2 measurements or signals. And your brain really consists of just one lonely unit, right? So again, we're very simple. We can only observe 2 things. So maybe we have like a left and right hand, and we can touch a surface with our right hand, touch a surface with our left hand, and we receive signals about how warm or how hot or how cold the thing that we're touching is. So we're feeling around, and that's all we can really observe are those 2 signals, right? So we have an input signal 1, which might be like our right hand touching something. Input signal 2, which might be like our left hand, right? And then we have a personal bias because we're all going to develop different notions of touching things because we're experiencing different data, and there's a bias to it, right? And then depending on these signals that we take in, we decide whether or not to lift up our hand or to leave our hands on whatever object we're touching. So there's some output signal that's like not generating, but telling us how to behave, right? So this is a kind of silly model, but it really does emphasize the point that as we take in these signals, it could be touch or vision or whatever, those signals are going to go into us and then make us act somehow, right? So to formalize this notion, suppose that we're given some labeled data, right? So we have feature vectors X. So each of these vectors X contains measurements. For example, how hot the right hand is touching thing, how hot your left hand is, or whatever. The X or the signals or the measurements, and the corresponding Y is the choice that was appropriate. So the label for those given inputs. So with that, we can now we can become a little bit more formal and say that now for this first input node here, we'll pass in the first feature from the vector X. Okay, so this is the ith vector in there. So this value, whatever numerical value is in that entry of the vector, is passed into the first input neuron or input node. I'll call it that for now. And then the second entry in that vector is passed into the second input node. And then instead of bias right here, we're going to input the numerical value 1. So the arrows indicate that those numerical values are going from left to right and passing into those nodes, and the nodes are going to store those values at a given instant, okay? And then we have something along the edges here, right? We'll come back to that in a moment, but there's stuff on those edges, and then these signals somehow come to you, and then you output a signal, which we'll denote by y hat superscript I. So the hat indicates that was the action that we chose. The superscript means that this is the action that we chose for the ith entry from this data set, okay? So these here on these first 2 edges are called the weights. Now, the idea behind calling them weights is that we're going to end up taking a weighted sum. So what's a good analogy? So suppose you have 2 input signals, and it's like your right hand on a stove, and the stove is slowly getting hotter and hotter. So that would be like your X1 input signal is the heat that you're feeling on your right hand on the stovetop as it's heating up. And then your other signal is say like you're holding an object, right? And it's heavy. And it's getting heavier and heavier. So someone's like putting like marbles in a jar, and you're holding the jar and you're trying to hold it as long as possible. Now, depending on how hot or how heavy the jar is, there is some combination that you should be able to withstand, right? Now, you might be more sensitive to heat, so you need a way of scaling the heat that you're feeling on your hand. And the way that you would scale that is with this number W1. So you have this input signal coming in and you're scaling it by W1. And maybe this is like really high because you're sensitive to heat. And even for low heat, like you need to take your hand off sooner rather than later, right? And maybe you're really strong and you can hold the jar at the same time and they can fill it with as many marbles as you want. So maybe this W2 will be pretty low, right? So you don't have to worry about this input signal as much as you have to worry about this input signal. So these numbers here, these are going to be numbers, are going to multiply the input signal. And then we're going to add a bias term, which is another number, sum all of those things together. And that sum is the signal that you observe as a person. Like you have two different things coming in, plus a little bias term, and you're trying to decide whether or not to stay where you are or drop everything around you. So take your hand off the stove and drop the jar. So it's like a yes, no decision right now. And it's all based off of the combination of the signals that you're receiving from the stovetop and from holding this heavy jar. Now that was kind of a silly analogy. I think it's better to actually look at a real example. And the example that we're going to use is this famous iris data set. It's one of the oldest data sets, one of the most used data sets in data science and machine learning. And it's a good example for a lot of algorithms. Now, anytime that I do, anytime that I implement an algorithm on the iris data set, I have provided all of you with this Palmer penguins data set. It's a very similar data set, and I encourage you to adapt what I do in class on the iris data set on your own with the Palmer penguins data set. So hopefully this weekend you'll write a perceptron algorithm or a single neuron model on the penguins. Okay, so this is the data set that we're going to use. And we're going to focus on two signals or two features for now. We can later in the semester focus on more, but for now, we're focusing on two signals. And the signals that we're focusing on, or the measurements, are sepal length of these flowers, these iris flowers, and sepal width. So X1 is sepal length, X2 is sepal width. And we're going to use these signals or these measurements to try to predict which flower that we're looking at, right? Now, just looking at this picture, you can see that, well, if the sepal length is above the sepal width, if it's above 3.5, then it's almost certainly looks like it might be a setosa based off of the data that we're looking at. In a similar fashion, if the sepal length is more than 6.0 centimeters, then it looks like almost surely the flower is a versicolor species, right? Now, those are kind of like the easy boundaries to find to say if it's over there, if it's over there. But what we really would like is to split this data completely like that. So this is what we're trying to do in this instance. In this case, we're taking sepal length and sepal width. We're trying to classify which species, setosa, versicolor. And the way that this looks mathematically is with, or not looks, the way that this is done mathematically is by finding what's called a separating hyperplane. This is, so imagine in three-dimensional space, there's a plane sticking up from this line coming at you, and it's separating the data into two distinct sets. If you find yourself on this side of the hyperplane, then you'll be labeled -1. If you find yourself on this side of the hyperplane, you'll be labeled 1. Okay, so again, there is some function that generates this hyperplane, and we're going to try to find it. And which means, since we're separating into two different species, we're doing classification, if that wasn't clear earlier. Okay, so we're ready to get started with the mathematics of the model. So we have this data. Each feature vector has a corresponding label. And well, what do we do next? Well, we're going to model a biological neuron. So this picture in front of you is a kind of dulled down image of a biological neuron, where this neuron takes in input signals and they flow through these dendrites into the cell nucleus. And then those signals pass along this axon, which is kind of dampened according to how it has learned in the past by this sheath thing. And then it outputs over here through the axon terminals. So it's almost like there's two stages here to this neuron. We're feeding in an input signal through these dendrites into the nucleus. And then there's like a processing of that signal before an output signal is given. So again, there's two stages: feeding in signal to the neuron, and then it's processed and then output. And that's the way that we're going to treat neurons. So here you can see that I've split my neuron into two separate parts and labeled the left-hand side Z. Z is called the pre-activation value of this neuron. So now we're making a neuron. This is an artificial neuron. We're actually doing it now. Now this pre-activation value, as you might have guessed, is the weighted sum plus the bias of the input signal at the ith data point. Okay, so it's just the weighted sum plus the bias. Okay, so that's the nucleus part, like feeding in. Now we have to kind of take care of the processing of the signal, which gives us A. And A is called the post-activation value. Okay, the post-activation value is found by passing the input signal into a function, phi. And this function is called the activation function of the neuron. Okay, so we have a pre-activation value, and then it's passed through an activation function, and then you have a post-activation value. And then with this model, that's going to be what we output. So y hat will actually be equal to A, which is the activation function applied to the weighted sum of the signals. Okay, so hopefully that's clear. Not clear, but at least like you're following along. This activation function is serving as the processing part of the biological neuron, but from an artificial standpoint. Okay, so we're starting to build a nice looking model. We have this artificial neuron here. We know what the pre-activation value is. We know what the post-activation value is, and that's what we output. So we should probably discuss what the activation function is. So depending on the choice of activation function, depending on the problem at hand, you will have a different selection of possible activation functions to choose from, right? So if you're in regression, if you're trying to do a regression model, you can choose a straight linear activation function. If you're trying to do maybe a probability output, then you would choose maybe like a logistic type of activation function. If you're trying to do classification in the binary classification, you might use something called the sign function as your activation function. And this is not the trig sign function. This is the sign function that is positive when the input is greater than 0 and -1 when the input is less than 0. And it's equal to 0 when z is equal to 0, but with our calculations, I can almost guarantee you that you'll never have a weighted signal input that is actually equal to 0. So we can just avoid that. This is our activation function. So, and with this choice of activation function, we can assign to setosa the label 1 and versi color flowers the label -1, or vice versa. Like, it doesn't matter. Just once you pick it, you have to leave it for the rest of the model. Okay.
Excuse me, I have a quick question.
Yeah.
So I know this is going back a little bit, but why do we have the hat notation on the Y? Does that denote like observation?
The hat is the output of the neuron.
Okay.
Without the hat, it's the actual label that we know.
Oh, okay. Okay.
Yeah.
I see. Cool. Thank you.
Yeah, just to reiterate that, if we look at the data that we're given, we have the Ys that are associated with the feature vectors. So these are pairs of data that we know, and we're generating a possible label for this input that then we can compare to the actual label. And we'll get to that in a moment.
Okay, that makes sense. Thank you.
Okay. All right, so we have more pieces now. We have the general model. We have two inputs, one bias, a single neuron, pre-activation, post-activation, an activation function. It's starting to look nice to me. So why would we use the sign function as our activation function? Well, the general idea is that if the weighted sum of signals is high enough, then we're going to fire. Otherwise, we're not going to fire. So if the neuron is deciding to fire a 1, that means that the weighted signals were high enough. The weighted combination of the input signals was high enough. And if it isn't high enough, then we don't fire. So we would spit out a -1. Okay? So if that weighted sum is greater than 0, the neuron says fire. If not, it says do not fire. So thinking back to the example of hand on stove and holding the jar with that's getting heavier and heavier, right? Like if it's not hot on your right hand and the jar is not heavy, your signals aren't strong enough to do anything different. But if either if the jar is way too heavy, or if the stove gets too hot, or some combination of both of them is high enough, then we're going to fire and say change, right? So that's the idea. In relation to the flowers, it's going to be the sepal length and sepal width. If that sum is great, this weighted sum is great enough, plus some bias, then we're going to say it's setosa, for example. And if it's not high enough, then we'll say it's first eye color. Okay. Now, if you're curious as to why the bias is there, we'll get there in a moment. Well, I guess we're here now. So this weighted sum here, right here. So Z is equal to W1 times X1 plus W2 times X2 plus B. This defines a hyperplane, right? This is a linear equation. So Z here would be a hyperplane, right? It's some three-dimensional plane. But if we set Z equals to 0 and we solve for X2, we can plot, so if we have weight 1, weight 2, and a bias, we can solve for X2 and we get this equation here. This is a function of X1, right? X2 is a function of X1. If we have the appropriate weights and bias and we plot this, it's going to generate this line. Okay. In the bias term, notice that this line is not passing through the origin. That's because we have a bias term. If this bias term was not there, we would not have the movement of the line would be restricted to pass through the origin. We need the bias term to move up and down so that we have some hope of possibly finding a line that splits this data. Now, it happens to be the case that this data in front of us is what's called linearly separable. There is a line that separates it, and I'm showing it to you right here. Okay. Not all data is linearly separable, but in this instance, it is. Okay. And there's ways to kind of check for the possibility of being linearly separable, and we'll get to that in another lecture. But hopefully you understand the bias. It's there to help move this hyperplane up and down on the X2 axis. All right. Oh, little remark on notation here. I don't know if you saw that change, but you will often write these linear combinations as just dot products. Okay, this is standard throughout all of these algorithms that we'll be covering. So W transpose times X, where W is the weight vector and X is the feature vector. And then we have this scalar B. Okay, so we haven't really talked about where the weights come from, right? And how this relates to the general framework that we built up earlier. Well, notice that W1, W2, and B, these are real numbers. So for any given choice of W1 and W2 and B, we're going to have a function that will make predictions on input features, input signals, right? For any choice of the weight vector in the bias term. And there's infinitely many choices, right? These are real numbers. So looking back to our framework, the hypothesis set in this model consists of all possible combinations of weights and biases. So what we're really doing when our algorithm is dipping into the hypothesis set is we're searching through all those weights and biases for the best ones that we can find to approximate the training data that we're using. And just to reiterate this, as function approximation goes, a single neuron is really a function which approximates f. And the performance of this neuron depends on how the weights and biases have been set or found. So after we've trained our model on the training data, or if we've like manually tweaked the weights and biases, we'll have a given weight vector and a given bias, and then we have a way of predicting a given label for a feature vector. So this would be our final approximation to f once we've tweaked W and B enough. Okay, so what's next? Oh, so we're getting started now with how we're going to find those weights. So when neurons are initialized, or born, I wrote, I don't know why I did that. The weights and bias are randomly chosen from some uniform distribution, from a normal distribution. Okay, so it's really important that these weights are taken from a normal distribution, and the same with the bias. So they're just taken randomly at first. And because of that, the initial outputs are either skewed towards one type of output, or it's just essentially random. The neuron doesn't know anything before you implement an algorithm to train the weights and biases, or manually tweak them yourself. So it's pretty much useless at the very beginning. But we can train it. And in order for our neuron to learn and to be trained better, we need a measure of how well the neuron is currently performing. So we introduce a cost function. Remember earlier I mentioned loss and cost functions, right? I happen to use C here instead of L, but this is the cost function that I'm going to choose. Now, if you're reading through textbooks, and with the exception of one, but if you're reading through most machine learning textbooks or reading articles online, and you look at a cost function for the single neuron model, which it has a name. Now that we've given it the activation function sign, we can call this the Perceptron model. So if you look at cost functions for this Perceptron model, it will not look like that. In fact, I don't think you'll see that cost function anywhere online. But trust me, there's a reason why I'm doing this. It is a valid cost function, first off. We have the square of the differences between the output and the actual label. So this is a positive number. This is what I'm scaling it by. I'm scaling it by a fourth. It's valid. It'll be equal to 0 if we're always getting the correct answer. And if we're always doing horrible, then it'll be really high. So it works. This works as a cost function. But I just have to warn you that this is not what you will see typically in the literature. And there are many other types of cost functions or loss functions that you can apply to this Perceptron model. Okay. Now that we have a cost function, we can talk about how to iterate a process to slowly have the weights get better and the bias get better. So again, there's our cost function. So recall that when we are looking at a feature vector xi, we feed it into the neuron in 2 steps. Take the linear combination, and then we throw that into the sign function for this Perceptron model. So for notational convenience moving forward, we're going to do something that is really common in machine learning. We're going to take our weight vector and just stack in or put at the bottom our bias term. See that bias right there? And we're calling this W bar. So that way we don't have to treat the bias separately. We can just say W bar has weight 1, weight 2, and then the third term would be the bias term. And when we do that, we also modify X. So X bar, we put a 1 at the very end of this vector. So this is the column vector X1, X2, 1. Now with this notation, we can easily write the output of our neuron y hat as the sine function applied to W bar transpose X bar, right? Hopefully you see that. Most of you should be familiar with linear algebra. The dot product of this vector and this vector is what? W1 times X1, W2 times X2 plus B times 1. That's exactly the weighted sum. That's what we pass into the sine function. This is what we're going to work with now. So it's just a notational thing that will become extremely useful later when we're dealing with hundreds of neurons and hundreds of bias terms. And this is important. Notation is very important, and there's a reason why we choose the notation that we do. All right, so now that we have that notation, we can talk about the update rule to better the weights and biases. So again, this is our output, and we're going to suppose that we predict the wrong label. There's two possible cases. Case one is that the label for xi was a 1, but the neuron says it's a -1. Case two, the label for the feature vector xi is -1, but our neuron spits out a +1. So these are the two possible cases for making an incorrect choice, right? So let's focus in on case one. The true label is 1, the neuron label is a -1. So what does that mean, right? If the neuron predicted -1, it means the sign of the weighted sum, the sign of that was negative, right? So it means that W bar dot X bar at the ith entry must have been less than 0, right? If we predicted a -1. But this should have been positive, right? Like we needed this weighted sum to be greater than 0 so that the sine function would say 1 and we would have got the right answer. So how can we fix this? Well, recall that the dot product of two vectors is equal to the norm of the first one times norm of the second times cosine of theta, where theta is the angle between W and X. Notice on the right-hand side of this equation, right? Notice that this is positive, so those norms are positive. The only possible thing that could make this dot product less than 0 is cosine of theta, which means that if this dot product is less than 0, then I know that the angle between them is greater than 90 degrees. Okay, so if we currently at the feature vector I, if we predict a -1, that means the dot product is less than 0, which means if we're looking at these vectors in space, that the angle between them is greater than 90. So here's the update rule. W is equal to W minus 1/2 the difference of the y's times x. It looks weird, but trust me, you're going to see this same type of thing over and over again. So let's just like see what this equals right now for this given scenario. Well, inside these parentheses, we have -1 minus 1. So inside the parentheses, this will evaluate to what? -2, right? And then that -2 times -1/2 is just going to be +1. So really, W is going to be moved to W plus X. So here's W, Here's x using this tail rule for addition. If I add x to w, this is my resulting vector. That vector is what we're going to change w to become. So now, after we've applied this update rule in this specific case, look at the angle between these vectors, x and w. The angle between them is less than 90 now, which means the next time we take the dot product of this weight and this x, it's going to be positive. The sign is going to predict a 1, and we would have got the correct label. We would no longer predict a -1, we would predict a +1. So this update rule, at least in this first case, seems plausible as a fix for our weights. If our weights are currently bad at xi and we want to fix them at xi, we apply this rule, the angle between the vectors gets smaller. Hey, this might work in this case, right? What about the other case? Where the true label was -1, but we wanted to predict a 1. Oh no, not wanted. The true label was -1, and our neuron predicted a +1. So it's bad. We didn't get it correct. Well, again, if we predicted a +1, that means that the dot product of our current weights and bias and that feature vector was greater than 0. But it should have been negative. We needed it to predict a -1, right? So, okay, we know that their dot product is greater than 0. The angle between them is less than 90. Okay. There's the same exact update rule. So what happens now? Well, let's see. Y hat is 1, and then y is -1. So 1 minus a minus. So inside the parentheses, we'll have a 2. 2 times -1/2 is -1. So this update rule in this case is w becomes w minus x. So if this was w right here, right? Did w appear? Where is it? Let me grab it real fast. Come back to my picture. Yeah, this is w right there. So going back to the update rule, I apologize for that. We see that we're going to modify w by changing it to be w minus x. So if here's w, there's minus x, and we add those together. This is the new vector that we get. And then there is the resulting w. And we fixed w bar. Look at the angle between them now. It's greater than 90, which means the next time that we encounter this xi, we're going to predict a -1. The dot product will be, now it'll be negative. The sign function applied to that dot product will tell us we should return a label of -1. So in both cases, this update rule works. What about if we always use this rule, even if we don't get it wrong? What happens? Right? Like if we do predict the correct answer and we still apply the update rule, what happens? Well, if we got the correct answer, y hat is equal to y, this whole term is 0, w just stays the same. So this update rule works even when we get it correct. So it works in both cases when we get it wrong, and it works when we get it correct, because if we predict the right answer, this is 0, we don't change anything about the weights. Again, for a given instance, xi. So this really looks like this vector image here, right? Like if currently we have like 2 inputs and 2 weights and a bias. So that's what it looks like. We can now split that into 2 different rules. And I'm doing this to relate it to something called gradient descent that we'll learn about next lecture. But for now, just notice that we can split this up as follows. So notice that the weights are just becoming what? The weight minus this term times x. So that's what this is right here. And then the bias is just bias minus this term times 1. So this is 1 right there. So this is the weight update rule, and this is the bias update rule, if you wanted to do those one at a time. Otherwise, you could just use the bar notation. So you can avoid the bar notation or use the bar notation now. So it won't be any difference. Okay, so now we should talk about how to implement this. So we're given endpoints of labeled data, so features and labels for each of those features. For each I, 1 to n, so for each of these values in here, feed forward the feature vector into the perceptron, the single neuron model, and get a predicted y value. And once you have that predicted y value, perform the weight perceptron update rule. So that's this rule here. And then update your bias with that rule. And repeat step 2 until either a maximum number of epochs has been reached, or the cost function is outputting a sufficiently small error. Now, what's an epoch? An epoch is one application of part 2. So if the number of epochs was 10, you would do part 2 10 times. You'd update the weights that many times. Okay. All right. So I think I'm going to pause the video